This is Roger Green, host of the Surfing the NASH Tsunami podcast. This weekend, we are offering 4 conversations from Season 3, Episode 17, our discussion on an exciting potential anti-fibrotic therapy of the future and other advances in omics. Scott Friedman starts this conversation by reviewing the historical sequence that led to the development of an mRNA vaccine that can create CAR T cells in mice for the express purpose of attacking fibrotic tissue. He discusses the parallel progress of 2 groups in utilizing CAR T therapy to destroy fibrogenic cells, one at Memorial Sloan Kettering in New York focusing on liver cells, and another at the University of Pennsylvania focusing on cardiac cells. He then describes how the Penn group, led by John Epstein, went on to integrate mRNA technology, the same one used in the Pfizer-BioNTech and Moderna's COVID-19 vaccines, to create a simpler way to manufacture CAR T cells in the body that kill fibrogenic cardiac cells in mice. First, congratulations to our friend Scott Friedman on his Lifetime Achievement Award. When you step back and look at where people like Scott and Neil Henderson are driving the science and technology of fatty liver disease, it taxes the mind's ability to absorb and envision all that change. I don't usually listen to our episodes more than once when we're done editing, but I've listened to this one 3 times so far just to absorb it. So, you're in for a treat. Sit back, listen, enjoy, learn, and when you're done, join the dialogue on our LinkedIn and Facebook discussion groups. With that, why don't we go on to the episode? We were originally going to devote this episode to talking about the work that has been done out at the University of Pennsylvania in combining CAR T and RNA as a way to deal with fibrosis. Now, that work's only been done in animals so far, but extremely exciting. We invited Neil on to comment on that, and then Jonathan Epstein, the author of that paper, unfortunately was unable to make it today. So we're going to try to hit 2 targets in one episode, which is Scott will start by talking a little bit about that work, and folks will comment on it. And that will, I expect, segue naturally into a conversation on some of Neil's work in single-cell genomics. As a guy who stopped taking a science course after high school, my guess is I'm going to listen and play traffic cop, but I'm expecting a fantastic episode. So, Scott, floor's yours.
Scott Friedman.
Whoa, the pressure's on. I'll do my best. So there have been a series of papers over the last 2 years that have opened the door to a very exciting new technology for treating fibrosis. To explain it, I need to give you a little bit of background. There has been efforts for several years now by many groups, but driven in large measure by fantastic scientists at University of Pennsylvania, to develop a specialized kind of cell therapy where you program the cell and turn it into a guided missile so that it will seek, find, and destroy specific kinds of liquid tumor cells or leukemias or lymphomas. I think mostly lymphomas. It's an arduous process, but it has saved a number of lives, and there are some patients who are alive over 10 years later. To apply this therapy, the technique requires that investigators take out some white blood cells from the patient who's going to receive the therapy and then introduce DNA to program them to express a specialized kind of receptor on the cell that ordinarily is not there. And that receptor endows this cell, which is a killing cell. It endows the cell with the ability to home in on its partner on specific cells. And by knowing that there are some specific type of markers on lymphoma cells, for example, they can design and apply or administer these specialized T lymphocytes to the patient, and the T cells, or what are called CAR T cells, because that stands for chimeric antigen receptor, or kind of a hybrid artificial receptor, these cells home in on the tumor cells and destroy them. It's really a guided missile. It's been a transformative in understanding and treating some very specialized kind of cancers. About 2 years ago, 2 different groups said, well, if it works for killing cancer cells, maybe we can think about using it to target cells that are making too much scar. And there are 2 groups that went about this. One I was peripherally involved with was from the laboratory of Scott Lowe and Michelle Sadelaine at Sloan Kettering here in New York. They were focused on liver. The other was from Jonathan Epstein, who's an exceptional cardiac or cardiology investigator at Penn. And both the Epstein and the Lowe groups did something conceptually very similar, is they said, let's try out a CAR T cell where we now program the cell to home in, not on a tumor cell, but on the fibrogenic cells in liver, which we know are called stellate cells. And parenthetically, I've been studying those since we first isolated them in 1983 or thereabouts. One of the secrets to this technology is what receptor do we home in on to make sure we capture and kill the right cells and not other cells. And in the case of the Lowe paper, which was published in Nature in 2019, the first author was Amor, A-M-O-R. They found through informatic analysis that there was a specialized kind of receptor called the urokinase plasminogen activated receptor, which is called UPAR, and they generated or designed this CAR T cell to home in on UPAR expressing cells, which it happens are largely, but not exclusively, specialized type of activated fibrogenic stellate cells. And what they showed is that if you induce liver injury in a mouse and you administer these UPAR-seeking CAR T cells, you can actually deplete the liver of those fibrogenic cells and reduce fibrosis. And at the same time showed that it can actually increase liver function, which raises some very interesting questions about how does fibrosis suppress normal liver function, and could the clearance of a subset of those fibrogenic cells actually unmask healthier liver and healthier hepatocytes. So that's example one. Example two was in the Jonathan Epstein lab. They decided to use a similar concept, but in their case, they looked for, or they generated CAR T cells that seek and find a cell surface molecule known as FAP1, or fibroblast activating protein 1, which happens to be expressed on a number of cells, but in the heart, which was his interest, it's expressed by related fibrogenic cells to stellate cells. And so conceptually, they did the same thing. They induced heart failure with scarring of the heart using phenylephrine and angiotensin, which are vasoactive mediators. They administered the CAR T cells that were sort of guided missiles, finding the cells expressing FAP1. And as in the liver example, they cleared the FAP1 expressing cells, they reduced the fibrosis, and they improved the heart function. So the conceptual novelty in both of those is the idea of pivoting from a cancer indication to an indication for CAR T where you're trying to deplete a cell that's causing disease that's not a cancer cell. Fast forward another couple of years, and Jonathan Epstein and his group, and I'm just an awestruck admirer, I have no role in these studies, but they did something that was even more clever, and they did it by leveraging not only the CAR T expertise at Penn, but also the now widely appreciated expertise in mRNA technologies. So to digress for a second, the Pfizer and Moderna vaccines, which we've come to know very well as perhaps the two most effective vaccines in the fight against COVID, are mRNA vaccines. So what that means is they're effectively a bag, a membrane, an artificial membrane bag that contains within it the coding sequence of an mRNA, so that once it enters the body, that mRNA is used as a template to create protein. And in the case of the COVID-19 vaccine, the mRNA encodes the spike protein, which is the most immunogenic part of the COVID vaccine. So the way those vaccines work is you administer the lipid nanoparticle containing the mRNA. The mRNA is translated into protein in the body, and that protein is expressed and ignites an immune response that provides some or a lot of protection against COVID-19 infection. So once again, Jonathan Epstein leveraged that technology to say, wow, instead of having to take those white blood cells out of the patient or out of the experimental animal, program with DNA that stably expresses a new receptor, and then put it back in the animal or in the patient, why don't we just give the instructions for that cell conversion into a killing CAR T cell by administering a lipid nanoparticle that contains the sequence to turn that white blood cell into a specific seeking vessel. So basically, all the work is effectively done in the body. So all one has to do in principle is administer the lipid nanoparticle just like you would the COVID-19 vaccine. Now the lipid nanoparticle translates protein and finds its way to the T cells and turns the T cell into a killing machine, specifically finding the same FAP1 molecule that they had validated before. And sure enough, when they administer what they call FAP-CAR, because it's the FAP1 CAR T cell, when they administer the FAP-CAR, lipid nanoparticles to mice with the same heart failure and fibrosis, they get the same result. But the advantages here may be obvious, but let me spell them out. Number one is you don't have to take cells out of the animal or eventually the patient. You're programming the cells in the body. So you can literally take an off-the-shelf lipid nanoparticle construct, in this case not for COVID-19, but to target CAR T generate CAR T cells. You can literally send it around the way we send around the vaccines for immunization. You could administer it and then let the liver and the body generate the CAR T cells, program those CAR T cells inside the body, and then find their way to kill the FAP1 expressing cells. So the one advantage, as I said, is it's off the shelf. The other advantage, which is not trivial, is that if you remember, I said the original CAR T constructs have integrated or DNA, and it's been shown now by Dr. Carl June, who's one of the pioneers in this field, that some of those patients that were administered CAR T cells for lymphoma 10 years ago still have some of those CAR T cells in their body, which is amazing. And of course, it keeps probably suppressing may keep suppressing the lymphomas that it was used to treat. But that also creates a problem because you've got cells that are engineered that are hanging around for a decade or more. The beauty of the FAP-CAR or the CAR lipid nanoparticle mRNA approach is that it's transient because mRNA turns to protein. mRNA can't integrate into the genome of the host, and so it will be self-limited. So So one could imagine giving a dose, seeing how effective it is, and then choosing a dosing schedule that allows you to kill some of those fibrogenic cells without permanently depleting them from the body or without taking too many out. So really fantastic technology. I think one can envision that this kind of mRNA technology for CAR T cells can also be applied to other diseases where there's a specific cell type. Could be an autoimmune disease, it could be other kinds of diseases where a specialized type of cell is wreaking havoc, and then you can zero in on it by administering a lipid nanoparticle CAR T and assessing the response without conferring a permanent implantation of an engineered cell. So I'm super excited about this technology, and hats off to the Penn group that again combined three world-class technologies, the CAR T, the lipid nanoparticle, and the mRNA technology, and they packaged it into a whole revolutionary new approach. Clearly a lot of work to be done, needs to be validated by other investigators and other groups, needs to show that it's safe. There is, of course, a long path towards getting this into patients and could be fraught and no guarantees, but conceptually and in terms of their first proof of principle, it's one of the most exciting things I've seen come around in a very long time.
So, Scott, thank you. Your typically elegant, eloquent, and fairly concise description of what's a pretty extraordinary piece of work. As I was listening to you, one of the reactions I had was, for years when you drove north out of Pennsylvania to Newark Airport, there was a billboard just before you got there from Prudential that said the first 150-year-old in history has already been born. And listening to that sequence of technology, you start to understand how people could get there in a way that we might not have previously.
Yeah, particularly as I didn't say it in specifics, but the Scott Lowe paper was focused on a marker that conferred senescence or old age on specific stellate cells. So your suggestion is actually more apt than you may have realized, because one could imagine clearing senescent cells on an ongoing basis. Pretty cool stuff. And I'm not sure I want to live 150 years, and I don't think I will, but that's a different discussion.
It is a different discussion.
Jörn Schattenberg.
My quick first comment is, Scott, thank you again for summarizing this so brilliantly. And I think you touch a very important point of the safety aspect. You built the argument that mRNA technologies might be more suitable because they have a more temporary or maybe more limited effect, which might be beneficial. On the other hand, the long-term effects in diseases like cancer or metabolic traits could be useful to have a baseline activity to suppress the ongoing metabolic inflammation. So case well built. There are arguments to study both approaches in these chronically ill patients. And of course, many things need to be saved. Since we have Neil on here, this is really the time to switch and ask him, as a clinician scientist, as I am, the same seat as you are, Neil. Of course, I'm wondering which cells to target or which conditions to address. And I think this is where we can hand over, or at least get your impression on here too, because you've seen these changes in single cells and deliver with your technology. And I think this will be very useful in this context.
So Jörn, before Neil does that, I totally agree. There's one comment I would like to make about safety, given that you brought it up. The biggest problem with CAR T and lymphoma right now is the high presence of cytokine response. In fact, depending upon what paper you read, somewhere between 12 and 20% of all patients have a level 3 or higher cytokine response storm as a side effect of CAR T therapy, which is why they are put in hospitals. You have to be certified by the manufacturer or otherwise to be able to administer CAR T. So it's rare and exceptionally expensive. And even then, as I say, 12 to 20% level 3 cytokine response, which is really inhibiting use. That's the real downside of having the cells stick around in the body, even for a few days, forget for a few months. And in fact, virtually all the work that you see being done in oncology right now in CAR T is on how do we minimize cytokine storm response. So if this is a solution to that problem, then it's not something you see in hepatology, but you do in some of the places I've worked in. It will be a big help going forward for that reason.
It's a great point. I actually just don't know if the FAP-CAR mRNA or the mRNA CAR T is less prone to cytokine storm. I think that's obviously something people are going to need to sort out. Maybe one of you guys know better than me the pathogenesis of that cytokine storm, but there's always a very long road as well.
And now, back to Roger.
We hope you've enjoyed this recording. If you have any questions or comments about the content of this conversation or the entire episode, please send an email to questions@surfingnash.com. We'll be back next week to preview May's Innovations in NAFLD Care 2022 meeting in Barcelona next month. Until then, stay safe, surf on, and we'll see you on the podcast. Bye-bye now.